Our next speaker here is Piyush Kumawat, and he is a PhD candidate at the University of Utah in chemical engineering. And he's also a graduate research assistant at the Energy and Geoscience Institute. He's currently a summer intern at the Idaho National Lab, but happened to be in town today to give this talk, so that's great. And there he's working on thermo-hydromechanical modeling of EGS reservoirs. His research focuses on DFN-based reservoir simulations, heat recovery optimization, and fluid flow analysis, particularly focused on the Utah Forge project. So his topic today is on comparative analysis of conceptual discrete fracture networks in enhanced geothermal systems. So welcome, Piyush.
Thank you, Eileen, for the introduction, and please welcome everyone and good afternoon here to run my talk. Today I'm going to talk about Utah Forge. It's hot. Everyone is looking towards it, like all renewable energy enthusiasts. Is this a real success? Like, can we get like energy really out of it? How long the reservoir will last? And it all depends on how we look at the reservoir. So there are different conceptual fracture networks that I analyze in this study, and I'm just going to walk through it during my presentation. Before that, let's quickly walk through about a brief introduction of Utah Forge. We have a site located in Milford, South to Utah. We have a couple of multiple monitoring wells and one injection well named 16A and another production well 16B. They all oriented towards east. Here we can see we go all the way down to 8,000 feet deep and touching the temperature of 225 C. Recently, the update we have is like we performed a stimulation in the lower section of the reservoir where we observed during the 10 stages that we performed stimulation. We got different hits that we can saw over there, and we can see that these the flow when we circulate fluid, it's going to take some flow path in the fracture network. So here we can I want to walk my audience to what activities I've been going through Utah Forge. It's challenging for me to summarize everything, but what I will focus on now is the data that we got to conceptualize the DFN networks. First, we had sorry for this font size, but I'm sure that the images will entertain you for a while. So we have here the site. We have 16A as injection well and 16B as a production well. First, we drilled 16A after a couple of monitoring wells. We performed a stimulation in that. We got some microseismic events going on there. And based on that, Utah Forge team decided to drill the second well, which is production well, 100 meters above the injection well. From that, we have well logs, borehole images to create a stochastic fracture network, how that reservoir looks like. Next, we performed a circulation test between the first circulation test, which happened last year in 23. And based on that, we have the microseismic data and flow distribution stages 1, 2, 3. Here's a stimulation of 16A, which was performed in 2024. We have this open hole section, stage 1, 2, and all the way up to 10. Again, we have the perforation locations and where we got hits in the production well. So we observed these hits from using DSS. We observed that there is a change in the strain when we stimulated the reservoir in over a particular section. For example, we stimulated stage 3R, which is we repumped the previously stimulated stages, and we saw, okay, we got hits over there, followed by stage 6, stage 7. We weren't able to pump some propant over there, but yeah, we did our job. We did stimulation. When we stimulated stage 8, we see a wide range of hits going on in production well. But when it comes to stage 9 and 10, we got repeated hits on the previous locations that we stimulated during stimulation of stage 8. So when we perform the circulation test, we saw that 70% of fluid is going to this region, this shared corridor of stage 8, 9, and 10. Then perform stimulation of 16B. The 16B is cemented, and so we performed stimulation to activate the heads we got over in the production well, so that fluid can circulate from injection well to production well. And then we performed a 1-month circulation test in August 24. Here we have like a bunch of data to create conceptual DFNs. So the motivation of this study is we don't know that how the geometry and fracture of network looks like, what's the pressure distribution, what's the thermal sweep efficiency, and how long the reservoir will last, the longevity, we don't know. And again, the challenge is as of now, there is no universally accepted way to conceptualize this fracture network. Is it like the simple planar fractures, fully coupled DFNs, and it is a data driven is required? What is it? And so there are like companies working like say ResFrac, Itasca, and Schlumberger. They are working on all of different with their different concept or how to look at the fracture network. But what I am here is to do is taking the perspective from all of them and putting all together, perform a finite element simulation, and see how much does it matter how we characterize the reservoir. So, and it will also have to assess the heat recovery performance, the computational expense, and to inform future DFN and modeling choices to EGS community. So the first DFN here is the 27 fractures. We have perforation location based on the stage 10 simulations. Say we don't know where we got hits, which fractures are contributing. So this is a traditional way of considering fractures. I consider all the fractures of equal size, like 150 meter in radius, and all the way from stage 1 to 10, 27 fractures I consider. Next, when we performed circulation last year, we got, only 17 of those perforations are taking fluid more than 1%. So I reduced that number from 27 fractures to 17 fractures. Next, when we talk about that, we got the DSS data that we stimulated one zone, we got a hit at another zone, and we saw that geology does matter. The hits are inclines towards the hill. So this DFN2 and DFN3 have 17 fractures. Conductivity is same in both the cases. The only difference is the fractures are oriented, which gives more heat transfer area between the injection and production well. Next, just to decrease the computational expense, instead of considering 17 fractures and accounting for only fractures which contribute more than 1% of fluid, the next one has only 13 fractures, where I scrutinize the fractures and remove 4 fractures and considering more than fractures which are contributing more than 2% of fluid. And then we have the fifth DFN, which is driven from microseismic data, well logs, core data, geological structure. Based on that, all credit goes to Dr. Alita Finila. She did a phenomenal job in characterizing these fractures. So we have 5 different DFN network. I'm going to compare all of them, perform a long-term simulation, see how long the reservoir will last. Sorry for going verbatim in this slide, but the whole idea is that there are different fracture count based on last 4 of these DFNs follow the flow distribution that we observed in the field, except for the first one. They say we don't know anything. We just have we perform simulation. Let's see. So this is how we mesh the reservoir. We take kilometer size, 1 kilometer cube size model. We put some fractures over there. So it's a 3D matrix with 2D planes representing fractures. If I compare all this DFN just for the finite element simulation, we see if we have like the DFN5, which is more geologically informed, the number of nodes goes high by like 10x compared to the other simple DFN I assumed, followed by the elements, degrees of freedom, and we can see the surface area is quite large in the fifth case of DFN. Now let's see the interesting results. So when we perform long-term circulation, I injected at 10 barrels per minute. That's what we injected during the last circulation test. And when we can see like if we perform like if we just inject at the same injection rate, 10 barrels per minute, at a constant temperature, we inject the fluid. That's how like we can see the temperature is going down. No matter how we characterize, how we see our reservoir, the temperature is not going to change by a scale of say 8 Kelvin out here. It's important for if we are looking for the like short-term circulation, we can see there is changes in temperature profile, wide variety from all the way say for different fracture network. But the interesting part we can see over here is if we have like inclined fractures or 13 planar fractures, whatever case, we see like all of them going to merge at the same point. So the key takeaway from this is, before going ahead, I'm just considering these 10 stages which are fractured in 700 feet of volume, and we are injected the same volume in that area. So it's only about how we look at the reservoir. So when we perform this the simulation, we are observing at the pressure at well 5832, which is right near close to stage 8. We observe that we are pumping some fluid, the reservoir is taking volume, it's getting pressurized, and that's how like we get the good pressure history match from the 17 planar fracture model, which is these two lines. Doesn't matter if they are inclined or not, we are getting a good match on the pressure. Now talk about the computational expense. As we see, like with increasing number of nodes, elements, degrees of freedom, the one with DFN takes longer time to compute. The time is over here in seconds. But the whole idea is if you are limited with the computational resources, GS2 they have a good amount of computation resources, so they don't constrain us to how we conceptualize the DFN. But if we are in the short of the resources, it would hardly matter. We can still see how these reservoir is going to perform. So now, like Department of Energy is and Utah Forge is planning to do 4-month circulation test. It's coming late summer. And we can see like over here, it's the 17 planar fracture model, which got the good history match in 5832. We see like these sections getting the near where we are injecting fluid, it's getting cooler. But when we go up to the production well, there is no much change in temperature over near the production well. If we go like after like 3 years, we can see that those areas are also cooling down. So the key takeaways from this is that fracture connectivity and orientation they do impact on the outcomes of EGS system. But if we are just concerned about the production temperature, see like after 10 years how it's going to last, we can choose the DFN that we can easily compute. I'm talking just about like finite element method over here. So for critical analysis of EGS, complex DFNs are recommended driven from geologic data and field data, which we have the DFN5 over there, which lasted the heat pretty long compared to the other ones. It has a larger surface area as well. But yeah, with limited computation resources, the longevity of reservoir can be approximated. So we don't need to go for too much details. If we have data-driven DFN models, no matter how we characterize the fracture, and if we are cooling the specific volume of the reservoir, we can approximately estimate what's the temperature going to be. That's what I got for today. Thanks to folks at EGI and INL for supporting my research. Thank you. That's all.